Hey guys, I'm Sophie, and today we're going to be doing a mini lecture on data structures. In this video specifically, we're going to go over the trees, so BSTs, B trees, and LLBRs. There's a separate video going over the other data structures like disjoint sets, heaps, and hashes. So if you have any questions, feel free to ask on Ed or even in the comments here. Jumping right into it, let's start with balanced trees. Nature lovers, where you at? Okay. So, what is a tree exactly? Let's get this understanding down. A tree is a set of nodes, and these nodes have a set of edges that connect the nodes from one another. One constraint, however, is that there can only be exactly one path between any two nodes. This means that trees cannot be cyclical. If a tree is cyclical, then it's not a tree, period. So what is a binary search tree? What makes a binary search tree different than just a regular tree? Well, BSTs have a specific property. For every node X in a tree, every key to the left subtree of that key is always going to be less than, and every key on the right subtree is going to be greater than. One consequence to this kind of rule is that no duplicate keys are allowed. This is because we're strictly comparing if it's less than or greater than, not if it's less than or equal to or greater than or equal to. Why is this concept so important? Well, it comes in handy when we're actually inserting a new node into a BST. Because no duplicates are allowed, the first thing you want to check when you're inserting a node is if the key already exists within the tree. If a key is found, then you don't do anything. If the key does not exist, however, that's when we want to actually create a new node and set an appropriate link. So in this example, let's say we were to insert eyes. We're going to start at the root. So we're going to compare eyes to dog. Eyes is greater than dog, so it's going to go to the right. Eyes is going to be less than flat, so we're going to go to the left. And eyes is greater than elf, so we are going to put it underneath elf to the right. So that's the concept behind insertion. You just go node by node, left to right, based off what the comparison is. Deletion, however, is where it gets a little bit trickier. There are three different cases when we are deleting a node. The first and most simplest case is if the node has 0 children. If the node has 0 children, all you could do is just sever the node. You just go in, let's say we're deleting alf, and just cut alf off from the rest of the tree. This is because it has no children. You don't need to worry about where the child would connect within the tree. You know that it already structures, like it follows the structure of a BST and doesn't break any rules, so you could just go and cut it out. The second case, what if it does have a child? What if it has one child? In this case, once again, because BSTs follow a specific set of strict rules, you could just replace the child of the node we're cutting to where the node originally was. What does this mean? Let's say we want to cut out ant. We cut ant out. We could just replace ant's child, Alf, to where ant originally was. So we just take bag, glue it onto Alf, and this is what the new node would look like. Once again, if you notice, this doesn't violate any of the rules. It still follows the greater than or less than structure, and it most likely will when we're cutting out one child. What about 2 children? This is probably the trickiest case, but we have a few set of rules in this case that'll help us make it easier to fix. So let's say we want to cut out the root. Well, if we cut out the root, we have 2 whole different subtrees to balance and to find a node that can replace it that won't break any of the rules. In this case, we actually have 2 options. The first option is the largest node on the left. So in this case, the largest node on the left-hand side of dog is going to be cat. So notice when we replace cat, or when we replace dog with cat, it does not violate any of the rules. Everything to the left side of cat is less than, everything to the right side of cat is greater than. The next option we have is actually the smallest node on the right side of the subtree. So the smallest node on the right side of the subtree would be elf. So if we replace dog with elf, this is what our structure is going to look like. And once again, it doesn't violate anything. This is a completely valid BST tree. One thing to note, when we're inserting and deleting new keys into a BST tree, we might get this sort of structure. This right-hand side subtree is what we like to call spindly. You could kind of think of it as like a linked list leaning towards one side of the tree. When we're talking about trees, we kind of want to keep a structure we call as bushy. Bushy is nice and even, it looks pretty symmetrical, the height is even throughout. We prefer bushy to spindly because it helps with the runtime and the iterations it takes to get from the root node to any of like the leaf nodes or the bottom nodes. So putting all this knowledge to practice, let's say we want to delete k, right? So if we want to delete k, remember, we have two options to pick from. The first option is the smallest on the left, or I mean the largest on the left, or the smallest on the right. So in this case, the largest on the left would be G, and the smallest on the right would be M. And these are our two potential options that won't disrupt the rules of a BST tree when we delete K. So remember when we were talking about the whole spindly bushy structure? Well, yeah, someone noticed that maybe inserting or deleting nodes causes that kind of imbalance. So they came up with a B tree, which avoids that imbalance when inserting a new node. A B tree, or specifically a 2-3 B tree, is what kind of helps this whole imbalancing issue we were facing. So the 2 refers to the number of items one specific node can hold, and the 3 refers to the number of children a specific node can have. This 2-3 structure helps ensure that the max height of the tree is going to be log n. So looking at this diagram to the right, this completely is a valid B tree because at most there are 2 objects in one node, and at most one node has 3 children. And once again, notice that this has a nice bushy structure. The height is symmetrical throughout, so it's going to take the same amount of iterations to go from the root to any of these bottom leaf nodes. So what about when we're actually inserting a new node? When we're inserting it, isn't this going to disrupt the height? Isn't this going to make it potentially spindly? Isn't it going to increase the iterations? Well, if you think about it, yes and no. When we're inserting something in a BST tree like we did before, we're going to start at the root. We're going to go down left to right, depending on if it's less than or greater than. And you want to follow that same kind of structure as in a B tree. But unlike BST tree, where let's say you're at a leaf node and you're like, okay, well, it's greater than, so we're going to make a new child and put it to the right. For B trees, what you want to do is you want to actually add it within that last leaf node. So what does that mean? Well, let's do an example. Let's say we're inserting 26. We're going to start at the top. 26 is greater than 17, so we're going to go to the right. 26 is greater than both 21 and 23, so we're going to go to the right as well. And 26 is greater than both 24, 25. But instead of making a new node down here and inserting it to the right of 24, 25, we're just going to pop it into the same node where 24, 25 is. This, however, violates one of the B tree rules. This violates that at most 2 objects could be in one specific node. But it's okay because we have a few steps to help us prevent this and to make this into a valid B tree. So if we look at step 2 over here, we have a condition. If the leaf node is full, what you want to do is you want to push the middle element up to the parent node, and we're going to split the current node. So hopefully by doing this is going to fix our problems and it's going to make this tree valid. But would you look at that? We popped 23 up. We split the 24, 26. I think we popped the 25 up. We split the 24, 26. But now not only does this violate the one rule where at most 2 objects could be in one node, now this violates that at most one node could have 3 children because this has 4 children now, right? But it's okay because we still have step 2 we could follow. We could repeat step 2 as many times as we want until we have a valid B tree. So we're going to do the same process. We're going to pop 23 up and we're going to split 21, 25. And let's see if this fixes anything. And this in fact does. This is a completely valid B tree. It doesn't violate anything, so we don't have to make any further steps. We don't even have to go to step 3 where if the root is full, we pop the middle element up, split the pop the middle element up, create a new root node, and split the current node. This also increases the height by 1. But we don't have to do that in this case because the root node has 2 elements, and that is completely fine because of that 2 structure. Notice when the 21 and 25 split, it took 2 children along with them. So no violations are made. The insertion operation is completed. We don't have to do anything else. Leave it as is. Looks good to go. Moving on to red-black trees. Red-black trees, or specifically left-leaning red-black trees, are really cool because not only does it retain the same properties of a BST with the less than or greater than aspect, it also has the same properties of a B tree. And this property is that 2-3 aspect. But looking at this diagram here, you're like, how is this a 2-3 tree? How does this retain the same property of a 2-3 tree, right? Well, that's where the colors come in. Black edges signify that it's a normal edge in a corresponding 2-3 tree. Red edges, however, imply the implicit connection between values in the same node in a 2-3 tree. That's a bit wordy. What does that mean? Well, looking at this, we see there are two red arrows. Red arrows basically signify that whatever the parent and the child is, so the 8 is pointing to the 7 and it's red, that means that those are the two objects within the same node. The same with the 4 and the 2. 4 and the 2 are going to be the two objects in that one node, and 1, 3, and 5 are going to be its children. This is how it retains the 2-3 structure. One other key note to remember is that red edges are only going to be pointing to the left. This is because this is a left-leaning red-black tree. So red edges on the left. So remember how we talked about that red-black trees have the same properties as a 2-3 tree? Well, technically, you could represent the same type of structure between 2-3 trees and red-black trees. So you could convert one to the other, and they both will mean and represent the same thing. So how do you actually do that? Well, if we're starting with a 2-3 tree, all you have to do is look at the stuff nodes. A stuff node is a node with more than one object. So in this case, since it's a 2-3 tree, a stuff node is going to be a node with two objects in them. Since this is a left-leaning red-black tree, what you want to do is you want to look at the left node, which is the 2. You're going to drop it down, and you're going to make it red. And that's going to take its children along with it. So drop the left node, make it red. Drop the left node, make it red. And this is how you get the red-black structure. So these are literally the same thing. It's the same it's the same object, different representations. So how do you go from a red-black tree to a 2-3 tree? All you have to do is you want to get the red node and you want to drag it back up to the node that it's connected to. So 2 is going to pop back up to the 4, and it's going to take the 2 children along with it. 7 is going to pop back up to the 8. So converting between trees is really, it's an important concept to understand because sometimes you're going to get a 2-3 tree or a red-black tree and you're going to be like, is this valid or not? And converting will help you understand if it is. So what are these rules that would violate if a LLRB is valid or not? The first rule is parents and children cannot both be red. This is where the conversion is really important if you understand it. So if a child and parent are both red, let's say in this example, let's say this arrow was also red. If we were to convert this tree to a 2-3 tree, that means the 7 and the 8 would both pop up to the 9, which signifies, hey, there are 3 objects in this one node. And guess what? That violates one of the 2-3 rules because at most only 2 objects could be in a node. So that's why both parent and child cannot be red. The next rule is red edges cannot be on the right-hand side. This is because it's a left-leaning red-black tree, so red edges are always on the right. And the last rule is every path from root to null has to have the same number of black links. This is, once again, we want to hold that nice and bushy structure. We want it to be symmetrical. We want the height to be even throughout because this helps with runtime. So yeah, you guys are going to be encountering some non-valid LLRBs, but do not worry, we have something called balancing operations to help us prevent that or to make a non-valid tree valid. The first rule is when we're inserting a link, the link always has to be red. This is because remember in BST trees when we're adding a new node, we're adding it to that leaf node. And what do multiple objects in what node signify when it's going to be an LLRB? Well, it's going to be red because it's that implicit connection, which is why we always want to add the node as a red node. But sometimes adding a red node is going to violate some of the rules. So how do we fix it? That's where balancing operations come into play. If a red node is on the right-hand side, you just want to rotate that node left. If the parent and child are both red, or if 2 red branches are in a row, you want to rotate them right and flip the colors. And if both children are red, then you want to flip colors. So let's put all these rules and balancing operations into practice, right? Let's say we want to insert 1. If we insert 1, it's going to go right there. It's on the left-hand side. It doesn't violate anything, so we don't have to do any balancing operations. We're good to go. What if we want to insert 23, right? Inserting 23 is going to end up on the right-hand side, and that violates a rule. Red cannot be on the right. So we just have to rotate it left, and that'll fix that. So 23 is going to pop up, 20 is going to come down, and the red link stays red. What about adding 9? What rule do we think this is going to violate? Well, 9 is going to go to the right hand of 4, but guess what? Now we have 2 children that are red, and that violates a rule. So that's when we color flip this entire subtree. So the red nodes turn black, and the black nodes turn red. What about 17? Hey, if we add 17, we're going to have 2 red in a row. This means that there's 3 objects in one node, and that's not good. That's not right. They're not following the rules. So we're just going to rotate all of this to the right. But that didn't fix anything because now we have 2 red children. No, thank you. We're going to color flip that. But wow, this just isn't working out for me. We have 2 red children again, but it's okay. Let's color flip it. And would you look at that? After all that insertion, all those things we inserted, we have a nice symmetrical tree. The height is even throughout. There's the same number of black nodes no matter which null node you want to go to. It has that nice bushy, even structure. It looks really good. And even if we turn this into a 2-3 tree, it's going to stay completely valid. Yeah. And everyone's favorite, asymptotics. So for all the data structures, all the trees that we have, BSTs, B trees, and LLRBs, there's 4 main, I guess, methods: insertion, deletion, search, and height. And all of these have a specific runtime. Add these to your cheat sheets. You never know when they're going to ask any type of asymptotics questions. It's just always nice to have it on deck and ready. Moving on to the actual worksheet, this is going to be Q3 on the final exam review session worksheet. So I believe the worksheet gives like a specific diagram. There's a dotted line. The dotted line signifies red. But one note, the diagram doesn't have anything to do with the questions. It's just trying to show you like what a red-black tree is supposed to look like, or like a potential example of it. These questions are more conceptual, basic, like general knowledge for it. So you don't have to refer to the diagram to answer any of these questions. And for all of these questions, they're going to give you a scenario, and they're just basically asking, hey, what color is this node going to be? So jumping right into it, you could pause the video because I will be going over the answer right after I ask the question. But yeah, so part A is asking, what is the largest value in a tree with more than one node? So what color would the largest value be? What color node is the largest value of the node going to be? So note that the largest value is always going to be on the right-hand side, and red nodes cannot be on the right-hand side. So by default, the largest value is always going to be a black node. What about the smallest value? What color is the smallest value of the tree with more than one node going to be? Well, let's think about this like we did for the largest value, right? The smallest value is always going to be on the left-hand side. And is there any type of restriction as to what color could be on the left-hand side? No. So the answer for this is going to be either. A 2-node 2-3 tree is always going to have a red smallest child, and a 3-node 2-3 tree is always going to have a black smallest child. Or the way I like to think about it is there's no restriction what color node is going to be on the left-hand side of a tree. What about a node whose parent is red? Well, if there's a child whose node, the parent is red, there's only one possible solution for this, right? The solution is going to be a black node. Because remember, if there are 2 consecutive red nodes, when we're converting it to a 2-3 tree, that means there's 3 objects within one node, which violates it. So if the parent is red, then the node has to be black. What about a node whose children are the same color? Once again, this would be a rule violation. So if 2 nodes of the same color are red, it's going to have to be a color flip. So it's going to end up being a black parent node. And there is no restriction on what color the node is going to be when it has 2 black children. So in this case, the answer is also going to be either. And lastly, what about a freshly inserted node after the operation is completed? The key phrase in this question is after the operation is completed. If it was just asking what's a freshly inserted node, the answer would be red, right? But in this case, because it's asking after the operation is completed, we don't know how many rotations or color flips this inserted node is going to be. So the answer is going to be even because you don't know, right? So yeah, that was it for the mini lecture. Those were all the trees we've covered. This was the question from the worksheet. Like I said, the rest of the data structures are going to be in a separate video. There is no worksheet question for that, so it's just a straight up lecture. If you guys have any questions, ask on Ed or ask them in the comments. And as always, good luck studying for finals. I believe in all of you. Thank you.